Welcome to the lecture 1 of Bivariate Gaussian Random Variables and sum of two independent random variables. Under a single random variable, we have seen if Z is a normalized Gaussian random variable, then the probability density function of Z, fz of Z, is equal to 1 by root of 2 pi into e power minus z square by 2. Here we will be seeing bivariate normalized Gaussian random variable Z1 and Z2. So for bivariate normalized Gaussian random variable Z1, Z2, the normalized Gaussian bivariate probability density function denoted as fz1 z2 of z1, z2 is defined as 1 by 2 pi into root of 1 minus rho z into e power minus z1 square minus 2 rho z into z1 z2 plus z2 square divided by 2 into 1 minus rho z square, where rho z is the correlation coefficient between z1 and z2. z1 and z2 are normalized Gaussian random variables, so z1 will be equal to x minus mu x divided by sigma x, where mu and sigma are the mean and standard deviation of x. X is the normal variable, z1 is the normalized Gaussian random variable, z2 is equal to x minus mu y divided by sigma y, where mu and sigma are the mean and standard deviation of the normal variable y. So z1 is the normalized Gaussian random variable of the Gaussian random variable x. z2 is the normalized Gaussian random variable of the Gaussian random variable y. z2 is the normalized form of y, z1 is the normalized form of x, so mu x and sigma x are the mean and standard deviation of x, mu y and sigma y are the mean and standard deviation of y, z1 and z2 are the normalized Gaussian random variable of the normal variable x and y. Rho z, the correlation coefficient, and we know from the earlier topic the correlation coefficient numerically lies between -1 and +1, so modulus of rho z will be less than 1, and z1 is the normalized Gaussian random variable of x. So if we see the mean or expectation of z1, then E of z1 is equal to E of x minus mu x divided by sigma x. So 1 by sigma x is a constant kept as it is into expectation of x minus mu x, where mu x is a constant. So it can be written as 1 by sigma x into expectation of x minus the constant mu x itself. We have seen this in the earlier module. If y is equal to ax plus b, then mu of y, expectation of y, average of y, e of y is equal to a into e of x plus the constant b itself. So here expectation of x minus mu x will be expectation of x minus this constant mu x itself. And expectation of x is nothing but mean of x denoted as mu x. So mu x minus mu x means 0. So this becomes 1 by sigma x into mu x minus mu x, which is 1 by sigma x into 0 or equal to 0. Similarly, Z2 is the normalized Gaussian random variable of y. So expectation of Z2 similar to this expectation of Z1, expectation of Z2 will be equal to 0. Now if we see the variance of Z1, variance of x minus mu x divided by sigma x, variance of x by sigma x minus mu x by sigma x, where mu x by sigma x is a constant. Here 1 by sigma x, the coefficient of x is constant. And we have seen in that a single random variable, if y is equal to ax plus b, then the variance of y will be a square into variance of x. So here variance of 1 by sigma x into x minus mu x by sigma x, which will be 1 by sigma x square into variance of x. Since this mu x by sigma x is constant, that is ignored. 1 by sigma x square into variance of x, and variance of x is nothing but denoted as a sigma x square. So 1 by sigma x square into sigma x square is 1. So variance of Z1, the normalized Gaussian random variable Z1 is 1. Similarly, variance of Z2 will be equal to 1. So variance of the normalized Gaussian random variable will be always equal to 1, and mean of the normalized Gaussian random variable are equal to 0. These points are to be remembered. Mean of normalized Gaussian random variable is 0, and variance of normalized Gaussian random variable is equal to 1. Next is the correlation of bivariate Gaussian random variable. So if we take the covariance of Z1 and Z2, then by definition, which you have seen in the previous topic, covariance of Z1 and Z2 is expectation of Z1, Z2, expectation of the product Z1, Z2 minus expectation of Z1 into expectation of Z2. Since Z1 and Z2 are normalized Gaussian random variable, expectation of Z1 and expectation of Z2 both are zeros. So this will be equal to expectation of Z1 into Z2. And by the definition of expectation of Z1, Z2 will be equal to the double integral from minus infinity to plus infinity. This product Z1 into Z2 multiplied with the bivariate Gaussian probability density function, the probability density function of bivariate Gaussian random variable fz1 z2 of z1 comma z2 dz1 dz2. In the previous slide you can see the probability density function of the bivariate Gaussian random variable z1 and z2 denoted as fz1 z2 of z1 comma z2. If we substitute that expression in this double integral and if we integrate, you get this as equal to rho z. So covariance of z1 z2 is same as if z1 and z2 are bivariate Gaussian random variable, then the covariance of z1 z2 is the same as expectation of z1 into z2, and which will be equal to the correlation coefficient rho z. Two-dimensional independent and uncorrelated Gaussian random variables. if the Gaussian random variables Z1 and Z2 are uncorrelated, this also we have seen in the last topic. If the random variables are uncorrelated, if the random variables are X and Y are uncorrelated, then the correlation coefficient between that random variables will be 0. So here we are considering bivariate Gaussian random variables Z1 and Z2. So suppose that bivariate Gaussian random variables Z1 and Z2 are uncorrelated, then the correlation coefficient between Z1 and Z2 denoted as rho Z will be equal to 0. So putting rho Z as 0 in the probability density function of bivariate Gaussian random variable, putting rho Z as 0, fz1 z2 of z1 comma z2 becomes 1 by 2 pi. The next factor is root of 1 minus rho z. Rho z will be 0, so that factor is root 1 or 1 into e power minus. Wherever you find rho z, if you put rho z as 0, remaining will be minus of z1 square plus z2 square divided by 2. 1 by 2 pi. 2 pi I can treat it as root 2 pi into root 2 pi. E power minus of z1 square plus z2 square divided by 2, I can split it that into e power minus z1 square by 2 into e power minus z2 square by 2. Here 1 by 2 pi as 1 by root 2 pi into root 2 pi. So 1 by root 2 pi into e power minus z1 square by 2 into remaining 1 by root 2 pi into e power minus z2 square by 2. And if we see this expression, 1 by root 2 pi into e power minus z1 square by 2 for a single random variable, for a single normalized Gaussian random variable, the probability density function is 1 by root 2 pi into e power minus z square by 2. So this is actually the probability density function of z1. Similarly, 1 by root 2 pi into e power minus z square by 2, probability density function of z2. So probability density function of z1, fz1 of z1, probability density function of z2, fz2 of z2. So you can see the bivariate probability density function of the Gaussian random variable z1, z2, fz1, z2 of z1, z2 will be equal to fz1 of z1 into fz2 of z2. That means z1 and z2 are independent. This is the condition for independence of two random variables. So this implies z1 and z2, which we have assumed as uncorrelated Gaussian random variables, are independent. So if bivariate Gaussian random variables are uncorrelated, then they are also independent. Uncorrelated bivariate Gaussian random variables are always independent. Next we'll see something about sum of two independent random variables. We have seen single random variable, we have seen bivariate random variables. Now we'll see sum of two independent random variables. Let x and y be two independent random variables and w be equal to their sum x plus y. Knowing the expectation of x, knowing the expectation of y, we can calculate the expectation of the sum W. Knowing the variance of x, variance of y, we shall say the variance of their sum W. So expectation of W, E of W is equal to E of x plus y. And we have seen E of, by linearity property, E of ax plus by is a into E of x plus b into E of y. So E of x plus y, which is E of x plus E of y. So expectation of y will be equal to expectation of x plus expectation of y. Mean of the sum W will be equal to mean of x plus mean of y. Then the variance of W, the sum W, denoted as sigma W square. By definition, it is expectation of W minus mu W whole square. This is the definition by which we calculate the variance of a random variable. So here the variance of the random variable W, denoted as sigma W square, is equal to E of expectation of W minus mu W whole square. Here W means it is a sum, mu W means it is mu x plus mu y. So expectation of x plus y minus of mu x plus mu y, or minus mu x and minus mu y whole square, which will be expectation of, will rearrange the terms, x minus mu x plus y minus mu y whole square. Inside the bracket you can write it in the form a plus b whole square, with a as x minus mu x, b as y minus mu y. So variance of W sigma W square is equal to expectation of x minus mu x whole square plus 2 times expectation of, inside the bracket, x part, x minus mu x whole square plus 2 into x minus mu x into y minus mu y plus y minus mu y whole square. Using that a plus b whole square, a square plus 2ab plus b square. Now use the linearity property of the expectation. This will be expectation E of x minus mu x whole square plus 2 is a constant kept as it is, 2 into expectation E of x minus mu x into y minus mu y plus expectation E of y minus mu y whole square. Now by definition, expectation of x minus mu x whole square means it is sigma x whole square, variance of x, plus 2 into expectation of x minus mu x into y minus mu y. By definition it is covariance of x comma y. You see, just refer the definition of covariance of x and y from the previous topic, plus expectation of y minus mu y whole square means it is a variance of y, sigma y square. Now since x and y are independent, again from the previous topic, we have seen independent random variables are uncorrelated. And whenever the random variables x and y are uncorrelated, covariance of x comma y will be 0. First of all, independent random variables are uncorrelated, and whenever the random variables x and y are uncorrelated, covariance of x and y will be 0. So for independent random variables x and y, covariance of x comma y will be 0. So here we have taken x and y as two independent random variables. So from the previous topic, covariance of x comma y will be 0. So putting covariance of x and y as 0, we get the variance of the sum sigma w square as equal to sigma x square plus sigma y square. So whenever you take the sum w of two random variables x and y, the mean of the sum, expectation of the sum will be sum of the expectations. Mean of the sum w will be sum of the means, mu x plus mu y. Similarly, variance of the sum w will be sum of the variance. Sigma w square will be sigma x square plus sigma y square. Now for that sum w, we shall see the probability density function. So the probability density function of the sum w is denoted as fw of w, which is equal to fx of x star fy of y, and fx of x star fy of y denotes the convolution of fx of x and fy of y. Convolution of two functions, which is also denoted as integral from minus infinity to plus infinity, fx of w minus y into fy of y dy, where this fx is the probability density function of the random variable x, and this fy denotes the probability density function of the random variable y. Or same formula, the convolution of fx of x and fy of y can also be written as integral from minus infinity to plus infinity, fx of x, the probability density function of x taken as it is, into fy of w minus x dx, where this fy denotes the probability density function of y. But in the integrand, we take it as fy of w minus x dx. Knowing fx of x, knowing fy of y, you can write what is fy of w minus x. So these two you have to substitute in the integral, then you need to complete the integration part. So remember these formulae for the probability density function of the sum w. If w is the sum of two independent random variables, then to calculate the probability density function of the sum, we use either the first formula or the second formula. Along with that, characteristic function of the sum w. In the first module under single random variables, you have seen the characteristic function of the random variable x, denoted by phi x of omega. But remember, it is also denoted as phi x of j omega. The notation for the characteristic function of the single random variable x, phi x of j omega. So here characteristic function of this w, where w is the sum of two random variables, denoted as phi w of omega, or also denoted as phi w of j omega, given by, if we take the notation as phi w of omega, then it will be the product of the characteristic function of x and y, phi x of omega into phi y of omega. Or if we take the notation for the characteristic function as phi w of j omega, then it is equal to the product of the characteristic function of x and y, phi x of j omega into phi y of j omega. So the characteristic function of the sum w will be the product of the characteristic function of the two random variables. Remember this. Remember the formula to find the probability density function of the sum and also the characteristic function of the sum. When W is the sum of two independent random variables. Now the exercise question. If x1 and x2 are bivariate Gaussian random variables related to other two-dimensional Gaussian random variables y1 and y2 by the relation x1 is equal to sigma x1 into y1 plus mu x1. x2 is equal to sigma x2 into y2 plus mu x2, where y1 and y2 are with zero mean and unity variance. Mean is 0, mean of y1 is 0, mean of y2 will be 0. Variance of y1 and variance of y2 are equal to 1. Obtain the covariance of x1, x2 and the correlation coefficient rho x1, x2. So x1 and x2 are two bivariate Gaussian random variables related to other two-dimensional Gaussian random variables y1 and y2. So both x1, x2 and y1, y2 are Gaussian random variables related by x1 is equal to sigma x1 y1 plus mu x1. Similarly, x2 is equal to sigma x2 y2 plus mu x2. Now you need to calculate the covariance of x1, x2 and correlation coefficient rho x1, x2. By definition, covariance of x1, x2 is equal to expectation of x1 minus mu x1 into x2 minus mu x2. By the relation given in the question, x1 minus mu x1 means sigma x1 y1. x2 minus mu x2 means sigma x2 y2. So it will be expectation of sigma x1 y1, sigma x2 y2. Here sigma x1 and sigma x2 are constant kept as it is into expectation of y1 y2. So see the formula of the correlation coefficient rho of two random variables xy. Rho xy is equal to covariance of xy divided by the standard deviation sigma x into sigma y. If you see the previous topic, there you will find the definition of the formula for correlation coefficient rho, which is equal to covariance of x and y divided by sigma x into sigma y. So from that formula, covariance So here we get covariance of x1, x2 as a sigma x1, sigma x2 into E of y1, y2, which is the correlation coefficient rho of y1, y2. Call it as 1. Now if you see, refer that definition of correlation coefficient rho x1, x2, which is covariance of x1, x2 divided by sigma x1 into sigma x2. This is the definition of the correlation coefficient between two random variables x and y. Using that we get this. Now here x1 and x2 are, or we get covariance of x1, x2 as equal to sigma x1 into sigma x2 into rho of x1, x2. Call it as a 2. This is from the definition of the correlation coefficient. Now refer that 1 and 2. Their left sides are same, so their right sides must be equal. In the right side we have the common factors sigma x1 and sigma x2 in both. So comparing 1 and 2, you gain rho x1, x2, the correlation coefficient between x1 and x2 as equal to rho y1, y2, correlation coefficient between y1 and y2. So question was find the covariance of x1, x2, calculated, find the correlation coefficient rho between x1 and x2. That also calculate. Next question. Let x and y be exponentially distributed random variable. Find the characteristic function and the probability density function of the sum w equal to x plus y. X and y be exponentially distributed. So probability density function of x, see that exponential distribution under single random variable, we have seen exponential distribution where we had the probability density function for x, fx of x is equal to lambda into e power minus lambda x for x greater than or equal to 0, 0 for x less than 0. Similarly, y is exponentially distributed, so fy of y is equal to lambda into e power minus lambda y for y greater than or equal to 0 and 0 for y less than 0. So since x and y are exponentially distributed random variables, the probability density function of x and y, fx of x and fy of y straight away can be written by using the definition of probability density function of the exponential distribution. Now take w as the sum x plus y. X and y are independent random variables, so the probability density function of the sum w denoted as fw of w is fx of x convolution fy of y, convolution of fx of x and fy of y. So use the formula integral from minus infinity to plus infinity fx of x into fy of w minus x dx. We need to substitute fx of x and fy of w minus x and then complete the integration part. Here fx of x means it is lambda into e power minus lambda x for x greater than or equal to 0 and 0 for x less than 0. Integral is from minus infinity to plus infinity with respect to x, so negative x values are also included in this. And definition says fx of x will be 0 for x less than 0. So if we consider negative x values, then this factor will be 0. So the whole integral will be 0. So ignore that negative factors. So you need to consider from 0 to. So that this can be replaced by lambda into e power minus lambda x. Now the second factor. Fy of y means lambda into e power minus lambda y for y greater than or equal to 0. So fy of w minus x becomes, replace y by w minus x, lambda into e power minus lambda into w minus x, provided y should be greater than or equal to 0. Here y means w minus x. So w minus x should be greater than or equal to 0, means w should be greater than or equal to x, means x should be less than or equal to w. So second factor fy of w minus x, I can replace it by lambda into e power minus lambda into w minus x, provided x is less than or equal to w. So x should be greater than or equal to 0, less than or equal to w. So this integral with respect to x should be from 0 to w. Then fx of x is lambda into e power minus lambda x and fy of w minus x is lambda into e power minus lambda into w minus x dx. Lambda square, lambda into lambda, lambda square constant kept outside the integral sign. Integral 0 to w, here e power minus lambda x into, you can split this and write e power minus lambda y into e power minus lambda x into minus x is e power plus lambda x. That e power plus lambda x into e power minus lambda x, which will be e power minus lambda x plus lambda x, e power 0, which is 1. remaining is e power minus lambda y dx. So since integration with respect to x, this e power minus lambda w can be kept outside the integral sign. Integral 0 to w dx. And integral dx is x, difference at the upper limit w, lower limit 0, which is w minus 0 or w. Lambda square into e power minus lambda y into w. Lambda square w into e power minus lambda y. This is for x greater than or equal to 0, x less than or equal to w. And since x is greater than or equal to 0, clearly w should be greater than or equal to 0. So fw of w will be equal to the probability density function of the sum of the x plus y, the probability density function of w. Fw of w is equal to lambda square into w into e power minus lambda w for w greater than or equal to 0 and 0 for w less than 0. The next part, characteristic function of w is phi w of j omega is equal to phi x of j omega into phi y of j omega. So we'll calculate both phi x of j omega, phi y of j omega, so that multiplying we get the characteristic function of the sum w. Phi x of j omega, which is e of expectation of e power j omega x by the definition of characteristic function, which is integral from minus infinity to plus infinity fx of x into e power j omega x dx, definition of the expectation. And here fx of x means lambda into e power minus lambda x, but for x greater than or equal to 0. So integral for remaining x values, for x negative, fx of x will be 0. So ignore the negative x values, consider only non-negative x values. X from 0 to infinity, lambda into e power minus lambda x, e power j omega x dx. Here lambda is a constant kept outside the integral sign. Integral 0 to infinity e power minus lambda x into e power j omega x. Base same, e power. So powers can be added, minus lambda x plus j omega x. We shall keep a minus outside the bracket. Similarly, x outside the bracket. So e power minus of lambda minus j omega into x dx. Lambda into. Now integration of e power ax with respect to x means e power ax divided by the coefficient a. Similarly, integration of e power minus lambda minus j omega x with respect to x will be e power minus lambda into j omega x divided by the coefficient of x, which is minus of lambda minus j omega. Difference at the upper limit infinity, lower limit 0. Now putting x as infinity, e power minus infinity will be 0. So the whole bracket is 0. Minus. Putting x as 0, e power 0 is 1. So 1 divided by, so lambda divided by this denominator minus lambda minus j omega kept outside the bracket. So it is a lambda divided by minus of lambda minus j omega. Inside the bracket we'll take the difference of this numerator part, e power minus lambda minus j omega x at the upper and lower limit. Putting x as infinity, e power minus infinity is 0 minus putting x as 0, e power 0 is 1. 0 minus 1 is minus 1, so there will be 2 negative sign, becomes positive, lambda divided by lambda minus j omega. In the same way you can calculate the characteristic function of y, phi y of j omega. Instead of x, now it is y. Rest of the calculations are similar to this. Just replace x by y. Right side no x nor y, so right side will remain, answer will be same, lambda divided by lambda minus j omega. Calculation is, integration part is similar to that previous one. Only changes to be made is, instead of x you have to take it as y. So now we have fx, phi x of j omega, phi y of j omega, characteristic function of x, characteristic function of y. Therefore the characteristic function of the sum w, that is phi w of j omega, will be phi x of j omega into phi y of j omega multiply lambda by lambda minus j omega into lambda by lambda minus j omega becomes lambda by lambda minus j omega square, which is the characteristic function of the sum w.